So it's time now to start to look properly at probability tree diagrams. I'm going to start to do some calculations here, and this is a very common problem for the UK GCSEs, as well as probably a lot of countries around the world. So, let's get to it. Consider the situation at the top there. This is two coins that have been tossed. Here they are, two separate coins. And here is a possibility space diagram for the outcomes. Now, if I said to you, what is the probability of getting two tails? You can do that from this diagram quite nicely, because the probability of each event, which we haven't got written down, is half, 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 half. Okay, so everything's equally likely. There's one option with two tails, so it's 1 out of 4 options. What about if I said to you, what about the probability of one of each? Right, let's come down here and do some calculations. Probability of one head and one tail. So straight away you see and you start to think about independent events. Well, the first coin, if I get a heads, I want a tails on the second. If I get a tails, I want a heads on the second one. So they are not strictly independent. Not when I want this particular combination. So let's have a look. Getting a heads and a tails is a pair of independent ones. Getting a tails then a heads so tails then a head, or a head then a tail, those are independent. Because what you get first doesn't change what you need next. So, to work out any of these probabilities, heads and then a head is just a half times a half, which is 1/4. But the probability of one of each, well, there's two different ways of doing it. So that's 2/4 or a half. Now let me go through that again. One of each is a head and a tail. If they're independent events, I'm just going to multiply the probabilities. But whatever I get on the first one changes what I want to get next. So this situation is not independent. However, a head then a tail is independent. Not one head and one tail, but a head and a tail. And then a tail, let's say. Head and then a tail. And the reason is that those two things don't affect each other. It's just a possible outcome. Well, that's quite a hard concept, and this is where a tree diagram can sometimes help. So the first toss of the coin gives me a heads or a tails, and we record the answers at the end. The second one is like so, and it happens no matter what. I write the probability for each outcome on the branches like this. And then I calculate the probabilities afterwards. So heads and a head, heads then a tails, tails and a heads, and then a tails and a tails. And you can see they're all the same, which we knew. So the probability of one head, let's put H, and one tail in 2 tosses, we know that's going to now be head then tail, tail then head. And you can follow the routes to help you see them. And so the probability will be 2/4. Now, let me write that even more carefully for you. The probability of one head and one tail in 2 goes is the probability of a head and a tail plus the probability of a tail and a head. And where the plus here means or, because it could be either way round. So it's 1/4 plus 1/4. So, what we've learnt in this part of the video so far, you write the probabilities on the branches. You multiply the branches to get the outcome. Then read what you were asked to find. So for example, the probability of one heads and one tails in 2 goes, and select all the branches that give you that answer. It might be helpful to write this down at the end to see that it's exactly the same as your possibility space diagram. Okay, now if I said to you now, what is the probability of at least one head, you could probably confidently say, well, that one, that one, that one. So it's that, add that, and that's 3/4. So, write the probabilities on the branches, label the events, event 1, and these two are the same event 2. Work out your probabilities at the end, label what they are, read the wording carefully, highlight the branches you want and collect them together. So, let's try one more. Here is a bag of balls. Okay, we're going to go through the same kind of process. I'm going to look at the probability of getting one red and one black in 2 goes after putting first back. Now, because it's 2 goes, whatever I get in the first go will change what I want in the second go. So, just because it says and, I can't just times these 2 together. Because the fact it's 2 goes changes it. Red would have to be followed by black. Black would have to be followed by red. So, choice is 1. Red and black. Red is 3 beads in the bag out of 7. Black is 4 beads in the bag out of 7. Now I'm putting the first bead back in the bag. Later on that won't happen, and that will change the probabilities later, but not yet. So red still is 3/7 and black is still 4/7 because it hasn't changed the bag. So the probability of 1 red and 1 black is, well, let's work out each branch first. That times that gives me 9/49 for red. 3/7 here times by 4/7 gives me 12/49 for red, black. Black, red, 12/49. And the last one, black, black, 16/49. Nine, 12, that's 21. Add that makes 33. Add that makes 49/49. So all of the probabilities add up to make 1. So 1 red and 1 black. That's here, 12/49, and here, 12/49. So that's 24/49. So draw the branches, label the outcomes, write the probabilities, calculate the end probabilities, label the outcomes combined, that's here, and then 6, read the question, combine the branches you need. You might want to write times in here to remind you that's where you're multiplying together. You might want to write an add here to remind you that's where you're adding them together. So this is the outline for how tree diagrams works. It is not everything yet. We've got several more to do in terms of layout, in terms of style, before we look then at worded problems. So in the next section, let's get trickier.